Thank you very much. So good day for everyone. On behalf of the Fields Institute and on behalf of the director, Kumar Murthy, and I would like really to thank today's speaker, Johannes, Dr. Müller, a professor from the TUM, the Department of Mathematics of Technical University of Munich. Dr. Müller is also directing the division of the biomass and biometric from the Hermes Center in Munich. That's a center that really feel strongly attached with that places a couple of places at time. And Dr. Müller is also linked to a few important research groups in Utrecht, Netherlands, and Tübingen. And I'm very glad he is coming today to talk about something I'm keen, and we are keenly interested on super spreaders and contact tracing. So I will leave the rest of the time for Dr. Müller. However, Dr. Müller has kindly suggested that if you have questions, you can always send questions through the chat. So we're going to keep monitor the chart so you can ask the questions during the presentation as well. Thank you, Johannes.
Thanks for the nice introduction, and of course also for the opportunity to present here something that's quite exciting, in particular as you are working the same direction. So I look forward to an interesting discussion. So again, interrupt me at any time point. Normally, if I would give a talk about contact tracing, I would start with explaining what it is, but I guess after a year of COVID-19, we are all experts, right? So I guess everyone here has on his or her smartphone a tracing app, and you know everything about contact tracing, so I can jump right away into the topic. The talk will be consist of three parts. So I will start with the basic model without super spreading, just to focus on the machinery, how to analyze the things. In the second part, I want to introduce super spreading and discuss a little bit how to handle that, that part. And in the last part, I would like to do some interpretation, and also, of course, at least for one slide, I would like also to look at SARS-CoV-2. So super spreading, contact tracing, first part. So we start with our hero of this talk, that's Heidi. Heidi is infected, but it's nice to say that it's not a serious infection, so it's quite happy. However, she is infected. And of course, she had been infected by her friend Maxi. So we have here an infectee-infector relation. Maxi is infector and infects Heidi. So that is indicated by an arrow, so a directed edge. But of course, Heidi and Maxi are not the only ones who are infected. So there are quite a number of people infected, but we are in the onset of the epidemic. There are not too many infected, and we have a large homogeneous population. Therefore, there's no chance that two infected persons have contact, and we get a tree. Sorry, we get a tree of infecteds. If we have a tree, then we can introduce generation. So that's our patient 0, who has generation 0. Then the infectees of patient 0 are generation 1. And so Maxi, this guy, has generation 2. Heidi, she has generation 3. That's not, of course, the complete story. Some people will recover earlier or later. But that's important to note. Even if, for example, patient 0 is recovered, we still count the generation starting with patient 0. So also if we have now here the recovered people who leave then this tree of infecteds, of course, if they are gone, still Maxi is generation 2 and Heidi is generation 3, right? So we keep this counting. But what we see is that due to since the people leave the tree, the recovered people, the tree is not a tree anymore, but a forest. So we have connecting components, which are trees, and there are several of them. So basically, until now, we have a birth-death process, a branching process, and the living individual establish a forest. And so we have a forest valued stochastic process. On top of this process, now we introduce contact tracing. So some person, in this case, Heidi, feels sick, visits the doctor. The doctor says, yes, Heidi, you're really infected. Tell me with whom you had contacts in the recent time. And so each person who had contact has a certain probability P to be named by Heidi, by the index case. And in a certain realization, well, she will name a few persons. So for sure, she will name her friend Maxi, the infector of Heidi, but also two other infectees. But this infectee is just missed in this realization. And now we have basically two possibilities. Either we stop here, that's one-step tracing, or, and that's we will focus at, the new discovered infected persons become a new index cases. And so we have recursive tracing. And in that way, we will find a complete connected component within the connected component of this branching process. So that's found since Heidi did name a few persons, and that yields then the detection of these guys. And of course, all these guys are removed now. And so we see we remove quite a number of persons at a time, and that introduce strong interdependencies. And of course, these dependencies, they make the process difficult to analyze, right? So if we again look at our process, we have a few parameters, not too many. So we have contact rate, beta, which depends on A, and A is always the age or the time since infection. So A is never the chronological age, but it's always the time since infection. And the contact rate, or better, the infection rate, of course, might depend on this time since infection. And we have two different recovery rates. One is mu, which might also depend on age since infection. The other is sigma. And the difference is that mu is for the asymptomatic recovery. So basically, people are not recognized as infected. So they recover, they will be never detected. Sigma is the detection rate. So perhaps you develop symptoms, or there is a test strategy to random testing that contributes to sigma. So with sigma, index cases will be discovered. And of course, we have additionally this tracing probability. So each edge of an index case has independently the probability P to get detected. So that's these are all parameters. And so we have something like a branching tracing process or birth-death tracing process. And I will often say birth for infection and death for recovery. So that's not really death. Of course, there are a lot of papers about contact tracing. And in the last year, that the literature did explode. And we can basically distinguish 4 different approaches. Simulation approaches, IBMs, that are, of course, very, very handy to discuss certain diseases. For the analysis, there is the pair approximation approach, which is basically a sophisticated mean field approach. Then we have the branching process approach, where we will discuss, and also Professor Wu is working there, at least that's what I understand. And there are the approaches which I call ad hoc or phenomenological approaches. So here people would write down an ODE, like the Kermack-McKendrick SIR model, and just phenomenologically add a term that's not rooted in first principles. They just claim that that would represent contact tracing. The nice thing is that they can be, these models can be readily discussed and analyzed. So they are really of value. But the disadvantage is that they are not rooted in first principles. And so we would like to have some specific idea of contact tracing and start from the scratch there. The very first paper I know about contact tracing is the one by Heathcote and York in 1984. They looked at gonorrhea. And already they did introduce an important concept that was backward and forward tracing. And also our approach to the analysis is based on backward and forward tracing. So what's backward and forward tracing? So we have always a focal individual, so our Heidi, our hero. And in backward tracing, Heidi can only be traced via her infectees. So the tracing goes in the opposite direction than the infection process, therefore backward tracing. In forward tracing, we again look at our focal individual at Heidi. She can be only traced via her infector, Maxi. So we go in the direction of the infection process. And full tracing is, of course, then that we can trace by the infector and by the infectee. And the nice thing is that in the analysis, we can focus first only on backward tracing. So we switch off forward tracing artificially. In practice, it makes no sense. So it's completely purely mathematically. That simplifies, of course, the process. Then we focus on forward tracing. We only go in forward direction with the tracing. And we will see that if we understand forward and backward tracing, then we can combine that quite easily to full tracing. How can we analyze the thing? We will always focus on the survival probability, so on the probability to be infectious at a certain age of infection, time since infection, and for an individual of a given generation, right? So here we would have 0 generation, first generation, second generation. So we would go to a second generation individual and would like to know how likely is it that Heidi, so a second generation individual, would be infectious after 3 days of infection, something like that. For backward tracing, we attach a minus. For forward tracing, we attach a plus. Full tracing is just this kappa I. So that's basically the target, to get this kappa I, because from there we have a lot of things at hand to tell something about the process. Okay, let's start with backward tracing. So again, we have here our Heidi, and we would like to know her kappa I minus of A. So we would like to know how likely is it that she is infectious after age of infection A. She can be only traced via her infectees. So of course, this probability satisfies an ODE. So the age derivative of this probability is minus kappa I times the removal rate. And we have here the removal rate for asymptomatics. We have here the detection rate, say, so that if you're sick, visit the doctor, are tested, whatever. And without contact tracing, clearly that's it. And we can work out kappa I minus. But with contact tracing, we have an additional contribution. That's the rate for removal by backward tracing. So we have here the infectees of Heidi. And in a certain age interval of Heidi, so A and A plus delta L, A, some infectee might recover. And if this guy recovers observed, then he or she could trigger a tracing event, and Heidi would be also detected and removed from the class of infecteds. And so we need that rate. The problem is that this might happen not only because this guy is directly observed, but it might be that this guy has also produced a secondary case, and this guy, the overnext generation guy, would be discovered, triggers a tracing event, and then in the second step also Heidi is traced. So we have to take into account for this this snowballing. How can we do that? So basically, we need, first of all, some information. How likely is it that such a guy is observed in a certain time interval, directly or indirectly? We start off with the hazard rate, so with the removal rate. So we know also for this, so Heidi has generation I, and these guys have then generation I plus 1. So in principle, we know the survival probability for the infectees of Heidi. And from that, we get in this way here the removal rate. Okay. And the removal rate has 3 contributions, or consists of 3 contributions. So first of all, we have the direct observation, so testing or whatever. Then we have indirect observation, which does mean that this guy is traced by himself, by his infectees. And we have spontaneous recovery. Spontaneous recovery will not trigger a tracing event for Heidi. So we are not interested in that. And so the rate for direct or indirect observation is the total recovery rate of the next generation minus the spontaneous recovery rate. So here we have the rate that we have a direct or an indirect observation. So we take into account the snowballing. And once we understand that, the remaining part is not really difficult. So here is the HA of Heidi. And so let's say this is times C. So Heidi has then HA minus C if she produces an infectee. So that's then the rate at which she produces an infectee. Then this infectee has to be alive or still infectious after time span C. That gives us this kappa I minus, I plus 1 minus of C. And then we have here the removal rate of this guy. And of course, it's not interesting for us when these infectees are produced. Therefore, we integrate between 0 and A. And of course, the tracing event has to be successful, that Heidi is really removed by contact tracing. And we look at the small time interval delta A. So we have here indeed the rate. So that's here the rate for successful contact tracing by infectees. And so we can add that in our ODE. So the derivative, the H derivative of the probability to be infectious, to be alive, to be infectious for Heidi is, oh, that should be an I, sorry for that, is minus kappa I minus spontaneous removal rate, direct observation rate, and the tracing, and that should be in close bracket. The problem now here is, of course, we have here generation I for Heidi, and here generation I plus 1 for the infectees of Heidi. So the system is not closed. We need somehow to close the system, but that's simple. That's indeed simple, because see, look, if we look at Heidi, she can be only traced via her infectees. If we look at the zero generation, we can the zero generation guy will be traced only by his infectees. So Heidi and this zero generation have precisely the same survival probability. Basically, the number of ancestors, the number of infectors, so that this guy has no infectors, and Heidi has two infectors, a buffer or infection chain of 2 buffer, that does not affect backward tracing, because only from the downstream individual tracing can happen. And so therefore we know that for all generation, the survival probability is the same. And so we can replace kappa I and kappa I plus 1 in our ODE by kappa 0. And we have a closed equation for the survival probability. So that's backward tracing. That's the first part. Then, after understanding how backward tracing goes, we proceed to forward tracing. Oops, no, here we go. The situation is slightly different in forward tracing. Again, our focal individual is Heidi, and she has the infector Maxi. And here we condition on the age since infection that Maxi had when he would infect Heidi. Okay, so we introduce kappa I plus A given B as a probability to be infectious at age since infection A. So that's basically here for Heidi. If her infector had as an infection event age since infection B. So Maxi had age infection B when he would infect Heidi. So that's a condition we set. And how can we get this condition probability? So first of all, we introduce kappa hat, which is the survival probability without tracing. So basically, if we take the tracing probability P to 0, no tracing at all, then for all individuals, the survival probability is this kappa hat is just e to the power of 0, integral 0 to A removal rate, dA. And so Heidi is now still infectious as her age of infection A, if she is infectious without contact tracing times the probability that Maxi did not trigger a successful tracing event, which is 1 minus Maxi did trigger a successful tracing event. So what we need to know is now in this time span here, how likely is it that Maxi somewhere recovered and did trigger a tracing event that removed Heidi from the set of infectious persons. Okay, once we are here, we basically do similar things and similar reasonings as we did before. First of all, we know that MAXI is infectious at age of infection B. We have to take that into account. And so if we ask how likely is it that MAXI is infectious at age of infection, at his age of infection B plus C, we have to divide by the probability that he was infectious at B, because for C equals 0, we know that the guy is infectious. So therefore, we have survival probability 1 at C equals 0, right? So that's just the conditioned survival probability, conditioned on the fact that he was alive at age of infection B. Then the next thing is, if he is alive at age of infection B plus C, that's the rate of direct or indirect observation of MAXI. That's the same argument as we had before. So, and from here, we just need to integrate over this time span for C from C equals 0 to C equal A to get the probability for a tracing event that triggers MAXI, and we multiply with P that the tracing event is also successful. And then we are done. So then we see that kappa I plus A of B, so the survival probability of Heidi, given that MAXI did trace her, infect her at age of infection B, is the probability that she's alive without contact tracing times the probability that MAXI did not successfully trace her in the time interval between 0 and A. Of course, we would like to remove here this condition. How can we do that? We have the information about the age distribution of the last generation, I-1, at infection. And we just integrate over to remove that condition. That's it. Okay, so that's quite simple, surprisingly simple. And now we would like to, in the last step, after we have backward tracing and forward tracing, we would like to combine that. And the combination is quite similar to this, this theorem. The only point is that we replace this kappa hat. That kappa hat, again, is a survival probability without contact tracing. And what we now do is the following. We have patient 0. So that's generation 0, patient 0. He has the survival probability of kappa 0. Since this guy has no parent, there can be no forward tracing. So the survival probability of this guy is given by backward tracing only. And now if we go to a certain individual, for example, to Heidi, to our hero, then we can conclude in a similar way as before, only that we say, oh, Heidi is either traced by backward tracing, so here she has to survive backward tracing only. And if we focus only on backward tracing, she is still in the same situation as the generation 0 guy. And so here is kappa 0, so this probability, times the probability not to be traced from her infector MAXI. So that's the very same structure as before. The only point we have to do is we have to replace the survival probability without tracing by the survival probability with backward tracing only. And the remaining part is the same. And so that's the central point of the complete game. So here we have a machinery working which can be adapted and can be used to look at different scenarios, different questions, and different models. The first question, of course, we have is what can we say over kappa I of A, over this about this function? Numerically, we see that this kappa I will converge rapidly. After 3 or 4 generations, practically is converged. Volker and me tried to prove that, and we used their contraction principle, and all we could find is a proof for the case that the tracing probability is sufficiently small. So if the tracing probability is small, this contraction principle would work. And in some weighted L1 space, we have convergence. but if p is too small, too large, we cannot prove it. So we are completely persuaded it converts rapidly, so you see it numerically, but we cannot prove that. That's an open problem. What we also have that converts to some kappa infinity, we can compute kappa infinity in case of constant parameters and mu equals 0. So that's an explicit formula. And in general case for constant parameters, but mu larger 0, so we have unobserved recovery, so asymptomatic cases basically. We cannot find out an explicit formula, but what we can do is we can expand kappa in terms of p, and we can readily get a first order approximation. And so therewith we can get approximate formulas for all kind of stuff. Next question, what did we do? What's kappa of A? So it's the survival probability, we understand that. It's important to understand that's the marginal survival probability. So basically, if we look at, let's say, kappa 3 of age A0, we simulate the process. We randomly select an individual of the third generation and check whether this individual is still at a certain age of infection, A0 infectious or not. And then we repeat it, and therewith we get an estimation of this, this probability. But that does mean that we have no information about all other individuals. So we have really a marginal probability distribution. No correlations are taken into account. We need to understand that to have a proper interpretation. What we can do is, of course, we can still define the reproduction number. So the expected number of secondary cases for a third generation individual, or if you take the generation to infinity, which is the asymptotics, where we are interested in this reproduction number. And that's a proper reproduction number. Normally, if you have the reproduction number, we have readily also a threshold theorem. Here, I have to say the threshold theorem is not really clear. Numerically, you see that everything works out. But since we have no control about correlations, it's difficult to prove in threshold theorem. So normally you would like to use something like the Golden-Watson process structure or something, but there it's important that each individual, once it's in life, acts independent of all other individuals. And here we have the correlations which make life difficult. However, the correlations, they decline very rapidly. So if we have a certain chain of infection, let's say 3, then each edge has probability p to be detected. And so to trace a path of length 3 has a probability p to the power of 3. So it's declining exponentially fast, this probability in the path length. And that does mean that the correlations decline really rapidly, and that makes that makes the thing work. Though again, mathematically, it's difficult. And in particular, the probability to extinction cannot be attacked in that way. So I think the threshold theorem is still okay, but to get the probability of the extinction, we need different tools. There are some papers, but up to a large degree, I think a full understanding is still also open. So again, correlations are really ugly. Okay, however, we have this machinery, we can address all kinds of problems. So we try to get some idea about how to estimate this tracing probability, which is of course an interesting thing. We can incorporate a tracing delay. So in the moment, our model has no delay in it, but everyone is removed at once. But of course, in practice, there's some delay. We can go into a model that is not homogeneous, but where we prescribe a contact graph. And if that is circle-free, so basically a tree, and we look at an SIR model, we can again get the exact thing to work. That it, I write Augustin, it's Augustin Oculi. That's his first name, sorry. That did a doctoral student of mine. And of course, we can try to get something like an deterministic model out of it. In the deterministic models, of course, you would like to also have a high prevalence. In the moment, we have been only in the onset of the disease, but ODE, chemical mechanic or something, you of course allow a high prevalence. Therefore, we need to replace the contact rate by a scaled contact rate. So only beta times S over N would be the rate of contacts to susceptibles. And then there are basically two different approaches. So we have seen we can define the reproduction number that we had. And so what we can do is we can introduce some nonlinear removal rate that would just give us the right reproduction number. And then we can have an SIR model with that nonlinear removal rate. And so we have an ODE. Second idea is to look at an age-structured model, where of course we use the hazard rate that we get from our analysis to describe the removal rate of this age-structured model. Again, age since infection, time since infection. And I think the group of Zhanhong Wu is working in that direction. At least that's how I understand. So I would like to understand similarities and dissimilarities in this point. Okay, so we understand more or less the simple model. And now let's introduce superspreading, which is of course interesting also for COVID-19. Superspreading can have several reasons. One reason could be an heterogeneity in the immune response. So some people have a weak immune system, therefore a high virus load, and then they are more infectious than other people. We could have an heterogeneity in the contact network. So typically for sexually transmitted disease, you would have commercial sex workers that have, of course, much more contacts than others. And so that they could form something like a hub in the contact network. But there's also a completely different mechanism of heterogeneity. So that's a temporal heterogeneity in the contact rate. So basically the idea is you visit a party, a birthday party, for example, and then for an hour you have a large number of contacts. And basically every person could do that. So that's no difference in the different persons, but it's difference in time in the contact rate. So mostly we are sitting at home in home office, have contact with our family. Once in a while we go shopping, but perhaps we are invited by our grandma to her birthday, and so we meet 20 people, and that could be something like a super spreader event. And so the difference is indeed that the first two types are some heterogeneity in individuals. And the last point is not a heterogeneity in individuals. All individuals are the same, but we have a random contact rate and heterogeneity in time. So that's different. Of course, also about this heterogeneity, sometimes it's called super spreading, sometimes only heterogeneity. There's quite a number of papers appeared. Particularly, of course, this seminal paper of Lloyd Smith, who introduced or who really wrote in the literature this importance about super spreading, and that viruses as SARS-CoV-2 or influenza have a high degree of dispersal, so super spreading plays a role. There are also many papers in the direction of heterogeneity and contact tracing. And most of these papers have the following idea. If our Maxi is a super spreader, then in the birthday party, he would affect a lot of people. And so it's quite likely that one of the infectees becomes soon an index case. This guy would trigger a backward tracing event, which identifies Maxi as a super spreader, and then we are likely to remove a lot of the other infectees. So this idea would indicate that contact tracing is even more efficient in super spreading events than in normal contacts. The second thing is that we need a combination of backward and forward tracing to cover super spreader events efficiently. Only backward tracing or only forward tracing will not do that. Also, there are a few papers appeared about COVID-19 that focus on that fact. But indeed, the literature is not really clear. So some simulation results indicate that perhaps super spreading could be not that easy to handle. So it's it's not really a unique opinion about superspreading or events like that and contact tracing, the efficiency of contact tracing. Okay, I will jump over that. So we will focus on this temporal heterogeneity because up to our knowledge, that's not that much investigated. And so we need a kind of model, of course. And what we do is we split the contact into two different aspects. So standard contacts. So in a certain time interval delta A, we have a certain probability beta 0 times delta A plus higher order terms as usual to produce one single infectee. So that's the standard thing, which we also considered in the first part. Then we introduce additionally super spreaders. That's slightly different. So again, in a certain time interval delta A, we have the probability for super spreader event, which is lambda times delta A. And if a super spreader event happens, we say then the number of infectees has a Poisson distribution with the expected number of infectees beta 1 over lambda. So here we have lambda and here we have beta 1 over lambda. That's to scale the effect appropriately. So basically in one single time span delta A, what's the expected number of infectees? So that's the probability for a super spreader events times the expected number of infectees, which is then just beta 1 over lambda. And you see that thing just cancels out, the lambda just cancels out. So in each time interval, delta A, we would have delta A times beta 1 secondary cases as the expectation, but the variance is of course higher than here in the standard contact rate. If lambda is large, what does it mean? Then the probability to have in a certain time interval a super spreading event is high, but the number of infectees is very low. So if lambda is really high, then basically the number of infectees is 0 or 1 because lambda beta 1 over lambda is tiny. And that does mean that we have in each time interval either 0 or 1 infectee, and we get indeed the structure of the standard contact rate with beta 1 of A as the contact rate. So if lambda is large, we basically are back in the standard case. If lambda is small, very, very small, then it's unlikely that a super spreading event happens. So most people will not have a super spreading event because they recover before a super spreader event happens. But if a super spreader events happen, then this beta 1 over lambda is huge. So we have a huge number of infectees. So basically, we can scale the model between the standard case and super spreading only in scaling lambda between large and small. Okay. Of course, this model can be now also slightly more formal. We want to introduce this contact rate, so this random contact rate. We need that later. So we have the Poisson process with rate lambda, and the arrival times of the Poisson process, the corresponding counting process. And we introduce this Z or ZA. These are just Poisson distributed random variables, which are all independent. And then if we look at a certain time interval, we can count the number of secondary cases. By standard contacts, it's just the integral over the contact rate and Poisson distribution of that. And for these, for the super spreaders, we have the times for the super spreader events. And if a super spreader event happens, then beta 1 at this time over lambda will give us the expectation of this Poisson distribution. And we can write it more elegant, the second term as an integral over the arrival process. But the important thing is that we have something like a random contact rate. So beta of A was before just a deterministic rate that we had in the first part of the talk. Now we have here a random contribution. So beta is a random rate, and each individual draws his or her own realization from this random function. Okay, so that's the idea. We can, of course, now analyze this model without contact tracing. I will jump over that to stay in time and rather focus on the ideas how to analyze this thing. Of course, it's more, slightly more complex. Recall the basic model that was for backward tracing, our result in the basic model. What we can do is we can take that as an inhomogeneity and use the variation of constant formula and represent this probability as an integral term. And here is our beta. Beta in the classical case is a deterministic function. Now we have a random function. So what we have to do is we have to take the expectation over beta, but beta is known. We have all these nice, nice properties of Poisson process and the Poisson distribution. And with that, we can compute the expectation and get an explicit expression, again, an integral expression for kappa 0. So the survival probability for the 0 patient for backward tracing. Similar idea for forward tracing. So there's no new idea in. A new idea comes in if we take backward and forward to understand full tracing. So where's that new idea? Before it was the following, we conditioned on the age of infection of the infector at infection. And then his or her survival probability had to be adjusted because we have this information that he was infectious at age of infection B, but that's it. Now it's different. So if we know that Heidi is an infectee at that time, it's likely that she is a member of a superspreader event. So she has co-infectees. And even if we exclude Heidi because we want to know her survival probability, therefore we basically remove Heidi and wait until she gets a signal that she's traced by Maxi. Maxi can be also traced by the co-infectees of Heidi. So that affects, of course, Maxi's survival probability. And so one central point is that we need to understand the number of co-infectees of Heidi. And that's an interesting point, which I learned. It's the only point I want to mention for this analysis. This question has been also raised in the context of multiplier games with a random number of players. And Meyerson, 1998, developed what he called the environmental equivalence property. So the idea is basically the following. So you have a lot of families. Each family size is Poisson distributed. And now what you can do is, of course, you can now randomly select a family. Then you get the Poisson distribution out. And if you say, okay, I want to have, so the co-members of one guy, that gives an ugly distribution. So basically Poisson distributed -1, something like that, conditioned on the fact that there's at least one family member. That's not what we are doing. We don't select a family, but we randomly select a family member. And so families with only a few members have, of course, a smaller chance to be selected than families with a lot of members. So the more family members, the larger is the probability that we just select a member of that family. And if we do that in this way and ask this guy, we select how many siblings do you have, then Meyerson could prove that this is again the very same Poisson distribution. And he could even prove under mild condition that the Poisson distribution is the only distribution that has this property. So in some sense, we have been lucky to assume that the number of infectees and superspreader events are Poisson distributed because that this theorem simplifies life a lot. In principle, it would be possible to go away from this assumption, but that becomes even uglier. But with that theorem, we can now get a theorem which parallels that we had before for this normal thing. We have here an additional step, basically, which is to compute the survival probability of an infector, given that we know this guy has an infectee where we need to take into account the chance that there are superspreader events. I don't want to now discuss these formulas. It's possible to draw a few direct conclusions, but also looking at the time, I should finish in 5 minutes as far as I understand. I would rush over a few interpretation, a few figures, and go via that route. So here we have the survival probability. So that's a logarithmic scale. For lambda large, that would be basically normal contacts. And lambda small, these are super spreaders. And the blue dash, so that's the 0 generation, first generation, second generation. So you see this convergence, even after 2 generations, not much happens anymore. This thing here is without contact tracing. The blue dashed line is theory. The solid lines are simulation, so it basically fits. And what we see if we have super spreaders is this sudden drop for the probabilities in the first and second generation. And that's precisely what we expected. So if we have super spreaders, then soon one guy is detected, the super spreader is detected, and a fraction P of the infectees are removed. And that happens very soon. And therefore we have this drop at very small age classes, this sudden drop. Next, we would like to look at the reproduction number. So what we see here. At the x-axis is the tracing probability. At the y-axis is our lambda, which does mean here we have basically normal contacts. Here we have super spreader contacts. And what we see is that we have here basically 2 regimes, so super spreading, normal contacts, and in between some transitions. We have 3 different probabilities for symptomatics, so basically for index cases. So here we have only few index cases. Here we have a lot of index cases. Use that as a substitute for testing, something like that. And now we have here a curve. And if we, for example, follow this curve, then on this combination of parameters, we have always the reproduction number 2.9, which does mean without super spreading, we need something like 0.65 as for the tracing probability to reach a reproduction number of 2.9. But with super spreading, we need only 0.3, say. And so obviously contact tracing is much more effective. We need a lower tracing probability with super spreading than without super spreading. So if our curves bend to the left, contact tracing is more effective with super spreading, as we discussed before. But what we see is that there are also curves that bend to the right. So there, contact tracing is less effective with super spreading. So we should investigate that closer. These are these 3 curves. So basically, we have here 2 scenarios with and without super spreading. We have a certain fraction of symptoms of index cases. And so basically, we have here 6 combinations. But with super spreading, we have all 3 realizations lie on top of each other. So we have that the reproduction number is basically linear, 1 minus p, linear decreasing in p, while it's nonlinear in the case without super spreading. And we can understand that. That is a clear hint that there are 2 different mechanisms at work. In the case without contact trace, without super spreading, what's the idea? We have a guy who infects persons, and if the probability for index cases is high, then soon there will be 1 index case, and with a certain probability, this guy will be removed. And basically, we prevent future cases. And so even if p is small, we might prevent a high fraction of future cases. In super spreading, it's different. So this guy infects a lot of infectees. Soon 1 or 2 will be index cases. So this guy is discovered, and we remove a fraction p of the existing infectees. Therefore, we have here the linear thing, and here we have the nonlinear thing. And so therefore, in particular, if we have a high number of index cases, without super spreading, we do better than with super spreading, right? So that's this different mechanism behind. And now we come to almost last slide. Of course, we would like to know how that's with SARS-CoV-2. We used some parameters of Tina Pollmann's work, and and added superspreading. Of course, we don't know really how much superspreading is there. Therefore, we have now no superspreading and superspreading. So the solid lines are superspreading, dashed lines no superspreading, and have a certain fraction of cases with and without superspreading. And what we see is basically most curves are very, very similar. Only if we have a lot of superspreaders and most cases are superspreading, then we approach a little bit this linear structure we have seen. But what we can say is that the influence of contact tracing on superspreading in the setting of SARS-CoV-2 seems not to be too important. So of course one has to be a little bit careful in the interpretation, but it doesn't not seems to be decisive. So it's not really a big disadvantage nor a big advantage, I would say. Yeah, so we are at the end. To sum up, what we have seen is we have two different kind of superspreaders. One is either superspreading is in the individual or in the contact rate. We can analyze that by the standard machinery, which we adapt. We find different mechanisms for contact tracing, superspreader event and non-superspreader events. I would like to mention one point. We always assume that all edges are traced independently. And of course, if you have a birthday party, your host would have a guest list. And so there would come in some dependencies. We don't understand in the moment how to do that, but that would be an interesting extension. So I thank you for your attention and hope for some questions, discussions, remarks.
Thank you, Johannes. So we're a very disciplined audience. Nobody raised the questions during your talk. So now we have the time. Anybody want to ask a question, you can raise your hand directly. We can unmute you. Maybe I can start ask the questions. Johannes says the north plot is I'm having trouble to understand this from more public health point of view. So if you have to do social gathering, I mean, with, for example, 100 people, you can run a super spread community event with all 100 people. You can also run a small gathering of 10 such event for each with 10 people. Then, so what are you trying to say? So you're saying it would be much easier actually to have a super spread event so that I can track the contact. I can throw the contact tracing to remove most of the transmission, the infections.
So the question, as far as I understand, is whether it would be possible, better to have a lot of small events,
so you
or
have
one huge event. Whether,
right. You have to have social activities.
Yes, sure.
So the big assumptions, and then so among these assumptions, you can have a larger community event, create a super spread event, or you can have number of small events.
Yeah.
Right.
So I could imagine that's somehow coded in this graphic here, because what we said is that lambda is basically scaling the size of the events, right?
Right.
And again, it really depends on the setting. What we have seen is that if we have only a small probability to have index cases, then obviously it's better to have huge events, because then you can be sure that some people are index cases and you can identify the super spreader event.
Right.
If, however, the fraction of index cases is rather high, or you do a lot of testing, right, which right. Would be a way to get that, then it might be better to have small events, because then only a few individuals are affected, but you still get them because the index cases, because you have enough index cases. So I think that's basically the answer. So it depends on how strong your testing. So for COVID-19, it would be how strong your testing strategy is. If you do a lot of testing, then small gatherings would be better. If you are lousy as we in Germany in testing, then probably you prefer to have a large event that you really can find out those of the large events that are dangerous.
Thank you. I will make sure to remove the video you criticize about German testing. I have questions from. I have a question from Jacques Belair.
So did I understand that super spreaders detection is not efficient in your next to last slide? You said finding super spreaders will barely have an influence, or was it the last one?
So yeah, that was in COVID-19.
Yes, this one. So unless you have lots of super spreaders.
Yeah. So therefore, I would like to go. I jumped over due to time. So thanks for the question, but I can go also to these two graphs. So we should understand that. So we can of course now investigate the effect of latency and incubation period, right? That's for in particular for COVID-19 important. And if you have only latency period, then the figure does not change. But if you have incubation period, so we start right away to infect persons, but we have a delay in finding persons, then the guys which we can remove in the super spreader event, they have already passed the infection. And so we are again back in this race to trace. And we see that the super spreader lines and the standard infection lines, they start to resemble each other. And so therefore, this interpretation which we had here is not appropriate if we have a large incubation period, because those guys, even those that we did find, would already affect the next generation. And therefore, since we have that in SARS-CoV-2, therefore we have not this benefit of super spreader events. That we are more efficient with super spreader events because we have this latency period.
So the detecting the super spreaders is linked to both this incubation period and the capacity in testing, right?
Yeah, so that's always the problem with SARS-CoV-2, that people start to infect persons before they show symptoms, and therefore the timing is very subtle in contact tracing, for sure, and so therefore it's not so efficient. So you can identify the super spreader event, you have a delay in that, and so your infectees will pass the infection already, and therefore it's not that efficient as you could hope for.
Thank you. The next one is from Andre Straka.
Hi. Do we hear each other?
Yeah, thanks.
Yes, okay, thank you. So two short questions. Firstly, if I understood correctly, when you mentioned the result of Meyerson related to siblings and Poisson distributions, does anything change if super spreading is not limited to siblings, but to some general colleague or any other types of networks?
So here we are in a homogeneous population, and so that was only an image to explain this thing from Myers. So basically, what we have here is we have a random variable y, which is Poisson distributed.
Okay.
And then we construct a random variable p, x is Poisson distributed, and then we construct y, which is not x minus 1 plus, which would be if we select each realization at equal probability, but the probability to get that k is k plus 1 times the probability that x is k plus 1 over. Then we have to normalize, of course. That's the way. So we select single individuals and not realizations. Is that clear?
So in principle, it doesn't actually matter whether they're siblings or anything else.
Yeah.
Right. This
Precisely.
is just a, okay, thanks. And just a very short additional question, more general one. You model this with branching processes. People, I think, model this in terms of random stochastic processes, also with other models like Neyman Scott and so others. Would anything change if you would choose a different type of stochastic process for your modeling of this is the very general question to your model?
So you go back to the very basic model as
Exactly, yeah,
as understand.
Yeah,
so what you can do is you can introduce a contact graph, right? And that's probably what you want to have to go away from the pure branching models. Then you have so you have nodes and certain degree distribution of nodes, and your epidemic process would run over this graph. And then of course you can also introduce contact tracing. That's possible for SIR models. You will know that an epidemic on a graph in general has you cannot analyze that. So if you have an SIS epidemic
Sure.
on a graph, then it's really difficult to get some insight.
Okay.
And so we run in that trouble. So even if the epidemic process has some difficulties, then to add contact tracing makes the thing not better. And so you can, so of course you can write down more realistic models, but I think it's really hard to get some analytic results. So the literature I did, so the literature I know, let's put it in this way. So I try to summarize that somewhere. So the basic approaches. So here, so all these guys. So here here we have really analytic results. These are approximate results, that's simulation, and this is not rooted in first principle. And what people do here is basically related in some way to branching processes. Okay. So I think it's hard to go away from that.
Thanks. Everything clear. Thanks a lot. Yes.
Thank you. Thank you, Andreas. And I want to again, first of all, thank you, Johannes, for coming this far to speak in these field seminars. And you may know that associated with the Fields Institute, a number of research groups with strong interest in branch processing and in the both serially and also in contact tracing modeling. So I believe I can speak on behalf of Kumar and Dr. Modi and the Fields Institute that we are very much interested to have more intensified discussions. So we will try to reach you and the audience that for some future events with a focus on the research project that Johannes touched today. And so also for audience, if you are interested in participating, contributing to such event, please feel free to contact me or the program manager, Sarah here. We'll try to organize something down the road when we have a clear plan what others are interested. With that, I want to again thank you, Johannes, on behalf of Fields Institute and the Canadian National Task Force for coming to talk to us today.
I thank you for inviting me and for the discussion, and I look forward to further discussions with you and your group. Thanks.
Great. Yeah, I see Thomas made a comment, so we are getting in touch. Thank you again.
Yeah. Thanks.